The universe, in all its staggering vastness, presents us with a question so simple it feels like a riddle from a child, but so deep that it shakes the foundation of everything we think we know about life, intelligence, and our place in the cosmos. It's called the Fermi Paradox. It begins not with telescopes or complex equations, but with a single logical observation. If the universe is so big and life has had so long to evolve, then where is everyone? Our own galaxy, the Milky Way, is a sprawling cosmic metropolis, an immense swirl of stars, estimated to contain more than 400 billion suns. Recent astronomical discoveries have only made this picture more astonishing. We now know that planets are not the exception, but the rule. Virtually every star we look at seems to have its own planetary system, and many of these planets are rocky, Earth-like, and orbit within what scientists call the habitable zone, the narrow band of distance from a star where liquid water, and by extension life as we know it, can exist. Think about the math. Trillions of planets, billions of years, conditions repeated over and over again throughout the galaxy. Even if life only evolved on 1 out of every million of those worlds, even if intelligent life arose on only 1 out of every 1,000 of those, there should still be thousands, perhaps millions of advanced civilizations in our galaxy alone. Civilizations that should, by now, be thousands or even millions of years more advanced than us. Civilizations that should have spread, signaled, explored, or left some kind of mark. And yet nothing. When we scan the skies with our most sensitive instruments, we don't hear alien radio waves. We don't see interstellar ships, Dyson spheres, or artificial megastructures. We don't detect signs of vast energy use, coordinated signals, or even a whisper of activity beyond our little pale blue dot. What we hear instead is silence, deep, total, cosmic. This is the heart of the Fermi Paradox, the eerie contradiction between the high likelihood of intelligent life existing elsewhere in the galaxy and the total absence of evidence that it does. It forces us to ask a question so profound, so unsettling, that it borders on existential horror. Why are we alone? The paradox is named after physicist Enrico Fermi, who reportedly asked the famous question during a casual lunch conversation in 1950. But where is everybody? At the time, the space age had not yet begun. We hadn't landed on the moon, launched satellites, or discovered exoplanets. And yet, even then, Fermi saw the contradiction. Given the size of the galaxy, even a modest spacefaring civilization should have had more than enough time to colonize the entire Milky Way. If they exist, they should be everywhere. If they don't, why not? To make the paradox even sharper, we consider how fast interstellar colonization could happen, at least in theory. A civilization doesn't need to send massive fleets to every star. It only needs to expand slowly, building outposts, sending robotic probes, or even just spreading signals. With conservative estimates of speed and time, a determined species could explore or colonize the galaxy in a few million years, a blink of an eye on cosmic timescales. But if someone did that, their presence would be unmistakable. We would see megastructures blocking starlight. We would detect unusual emissions or anomalies. the galaxy would hum with artificial patterns. Instead, the data shows nothing. Not a whisper, not a trace. So, where is everybody? Some say it's because we're too early. Others say we're too late. Some suggest we're not interesting enough. Others propose we're being deliberately ignored or actively hidden from. But all of those are just possibilities. Before we dive into the theories, we must fully grasp the gravity of the paradox itself. Because this isn't just a scientific mystery, it's a challenge to our understanding of ourselves. Either we are the only spark of intelligent life in a galaxy of silence, or we are one of many, and something is stopping us from hearing the others are becoming like them. The Fermi Paradox is not just a question of science, it's a question of identity, of philosophy, of fate. It asks whether our intelligence is common or rare, our civilization typical or unique, our future promising or doomed. It is the mystery that haunts every attempt to answer the most ancient question humans have ever asked when they've looked up at the stars. Are we alone? And if we are not, why has no one said hello? In the parts that follow, we will explore every possibility, from the terrifying to the hopeful, from scientific to philosophical, from cold equations to cosmic destiny. Every idea is a thread in a tapestry that might explain the silence. But first, we must sit in that silence, understand its weight, feel the contradiction between probability and reality, and truly appreciate just how strange and special it is that we are asking this question at all. Because perhaps the real paradox is not the silence we hear out there, but the fact that we're here to notice it. The silence of the cosmos is haunting. But what if it's not surprising at all? What if, instead of being surrounded by countless civilizations that haven't contacted us yet, we're surrounded by nothing? Not because intelligence is rare, but because life itself is almost impossible. That's the heart of one of the most sobering solutions to the Fermi Paradox, a concept known as the Great Filter. The Great Filter theory suggests that at some point along the path from lifeless matter to a galaxy-spanning civilization, there is an almost impossible barrier, something so unlikely, so devastating, or so universally fatal that almost nothing gets through. And the very first possible filter, the origin of life itself. This is known as a biogenesis, the transformation of non-living matter into a self-replicating living organism. And while it's the first step in any biological journey, it may also be the hardest. Imagine the early Earth around 4 billion years ago. The planet was still violent and unstable. Meteors bombarded its surface. Volcanoes erupted constantly. Radiation from a young, angry sun rained down in waves. The oceans churned with organic chemicals. Lightning storms flashed overhead, and the land was barren rock. It was a chaotic chemical soup. But somewhere in that storm, something remarkable happened. Chemistry gave rise to biology. That moment when atoms arranged themselves into molecules that could copy themselves is the single most important leap in the history of life, and it might be unimaginably rare. You see, life isn't just a matter of mixing the right ingredients. The universe is full of those. Carbon, hydrogen, nitrogen, they're everywhere. The challenge is putting those atoms together in exactly the right structure, at exactly the right time, under exactly the right conditions. It's like dumping out a box of watch parts onto the floor and waiting for an earthquake to assemble them into a working Rolex. Not impossible, but statistically, vanishingly improbable. Let's break it down. For life to begin, several mind-boggling things have to happen in the right sequence. Simple molecules like amino acids and nucleotides need to form from basic elements. Those molecules must link into complex chains proteins, RNA or DNA, that can store and copy information. These chains must be protected by a membrane, like a cell wall, to keep their internal environment stable. The protocell must have a metabolism way to gather energy and use it to maintain itself and replicate. Each step is hard, all of them together, astronomical. And once life does emerge, if it does, it's still just the beginning of the story. Evolution takes over, yes, but only if the conditions are stable enough to let it happen. A single mistake, a single extinction level event, and it's all over before it begins. That's why some scientists believe abiogenesis might be the great filter. They propose that it's so staggeringly unlikely for a living cell to form from non-life that it might have happened only once in the entire galaxy, or maybe once in the entire observable universe. In this view, Earth is not just a rare planet, it's a cosmic miracle, the only place where the dice landed just right. If that's true, the silence of the universe isn't surprising, it's expected. It's not that other civilizations are hiding, it's that they never existed in the first place. Their oceans are sterile. Their planets are lifeless. The conditions were right, but the spark never came. In this scenario, we are not just lucky, we are alone. Completely, totally, uniquely alone. But that idea, while humbling, comes with enormous implications. Because if the great filter is behind use, if life itself is the hardest step, and we've already passed it, then perhaps the road ahead is more open than we think. Perhaps we really are the first spark in a galaxy of darkness, and it's our responsibility to carry the flame forward. Still, it's worth remembering, we don't actually know how abiogenesis happened on Earth. Not really. We have theories, yes. Some scientists propose that life began in deep-sea hydrothermal vents, where minerals and heat could have catalyzed the formation of organic molecules. Others suggest shallow tidal pools, where wet-dry cycles might have concentrated amino acids into long chains. Some even think that life's building blocks came from space, delivered on comets and meteorite swots known as panspermia. But none of these theories have been confirmed. Not one has reproduced the full process in a lab. Despite decades of research, the origin of life remains one of the greatest mysteries in all of science. That mystery leaves room for awe, but also for fear, because until we find life elsewhere, until we see it arise independently of Earth, we simply can't know whether we're common or singular. And if we are singular, if abiogenesis is the great filter, then the silence of the universe isn't a puzzle to be solved. It's a message. A quiet, distant message whispered across the void. You are the first. Let's imagine for a moment that the first great leap of abiogenesis wasn't the hardest part. That the spark of life does, in fact, emerge on many planets across the galaxy. A few organic molecules link together in just the right way. A primitive cell forms. It begins to replicate, adapt, evolve. Surely, from there, the rest is inevitable, right? Not exactly, because even after life emerges, there may be another filter waiting, one not based on improbability, but on fragility. This is the concept of the early bottleneck, a second kind of great filter that doesn't stop life from forming, but prevents it from surviving. We often think of life as robust. After all, it's existed on Earth for over 4 billion years. It's crawled from the oceans, walked on land, soared into space, but that resilience is deceptive. In its earlier stages, life is not strong. It is delicate, vulnerable, and the planet it arises on, far from gentle. In the early history of any world, chaos reigns, new planets are volatile places, volcanic eruptions, meteor impacts, fluctuating climates, unstable atmospheres. These are not minor events. They are cataclysms, and life, in its infancy, is no match. When primitive organisms first begin consuming nutrients and producing waste, they do something dangerous. They start changing their environment. And without balance, without feedback loops or evolved checks, those changes can quickly become fatal. This is what the Gaian bottleneck theory suggests, that most biospheres destroy themselves before they stabilize. The very act of living becomes the cause of extinction. We don't need to look far to find a real example. On Earth, about 2.4 billion years ago, a group of newly evolved microbes began using sunlight to split water molecules. In doing so, they released a waste product that was toxic to almost all existing life at the time: oxygen. At first, oxygen levels were low, but over millions of years, these photosynthetic organisms pumped more and more of it into the atmosphere. Eventually, it triggered a mass extinction event, now known as the Great Oxidation Event. Nearly every anaerobic species on the planet died. Earth was nearly sterilized by its own children. We survived, but barely. What if, on most worlds, that balance is never found? What if life arises, begins to flourish, and then wipes itself out before it can evolve beyond microbes? Maybe the oxygen crisis on Earth was one of many close calls. Maybe Earth is a statistical outlier planet where early life got lucky. It stumbled through its first extinction event, adapted, recovered, and slowly began evolving into something more. But on most other planets, the story ends differently. Life emerges. A few simple organisms begin to change the chemistry of their oceans. Temperatures rise or fall. The balance is lost. The ecosystem collapses. And the experiment ends before it even truly began. No fossils, no civilizations, just a graveyard of sterile oceans beneath a calm, lifeless sky. This kind of filter is subtle. It doesn't leave ruins. It doesn't make noise. It's not dramatic, it's quiet, clinical, and final. It's a reminder that evolution doesn't just require time, it requires stability. A planet has to survive billions of years without being wiped clean by its own geology, atmosphere, or climate. And the odds of that happening might be far lower than we think. Even on Earth, the path was treacherous. In the early days, our planet endured multiple snowball Earth events, global glaciations that may have frozen the oceans from pole to equator. Later, we faced supervolcanoes, gamma ray bursts, and asteroid impacts, each one a potential reset button. And yet, life held on, somehow. It didn't just persist, it learned to regulate. Over time, Earth developed complex, self-correcting systems. Volcanic eruptions released carbon dioxide that warmed the planet. Plate tectonics recycled nutrients. The carbon silicate cycle kept temperatures in check. Eventually, life itself became a stabilizing force. It was only after this balance emerged that evolution was able to flourish, that multicellular life appeared, that intelligence eventually evolved. But if the Gaian bottleneck theory is correct, then most planets never reach this phase. They flare with life, like a match struck in the dark, and then fade. This theory redefines our search for aliens. It shifts the focus from finding life to finding stable life. Planets with biospheres that didn't just emerge, but learned to survive themselves. It makes our own world feel not just special, but almost impossibly fortunate. Because if the early bottleneck is real, then the silence in the galaxy isn't just the absence of advanced civilizations. It's the silence of a million failed experiments, of planets that gave life a chance but couldn't carry it forward. We are not just rare, we are survivors of the second filter, and in that survival, we've inherited an incredible responsibility, because the silence out there might not be caused by distance or time. It might be caused by something far more tragic. They didn't make it. So far, we've explored the possibility that life is extraordinarily difficult to starter, even harder to sustain. But what if life itself is common? What if microbial organisms are bubbling beneath the surface of Martian ice, swimming in the oceans of Europa, or drifting unseen in the clouds of alien worlds? It's not life that's rare, then. It's us. This is the unsettling possibility known as the rare Earth hypothesis. The idea that simple life may be everywhere, but complex, intelligent life like ours is astronomically unlikely. The conditions that allowed humans to emerge might not just be uncommon, they might be near impossible to replicate. At first glance, Earth doesn't seem especially unique. It's a rocky planet in the habitable zone of an average star. It has liquid water, an atmosphere, and a magnetic field. But once you start adding up the fine details layer upon layer of astronomical coincidenza, different picture emerges. Let's begin with our sun. It's not just a star, it's the right kind of star, a G-type yellow dwarf, stable and long-lived. It provides consistent energy without the violent flaring seen in smaller red dwarfs, and it won't burn out for another 5 billion years. Red dwarfs, which make up the majority of stars in the galaxy, often bathe their planets in deadly radiation. Blue giants burn too fast for life to evolve. We lucked into the sweet spot. Next, consider our orbit. Earth sits precisely in the sun's habitable zone, where temperatures allow for liquid water to exist on the surface. Not too close, not too far. But more than that, our orbit is nearly circular, keeping our seasons mild and stable. Many exoplanets have highly elliptical orbits that swing wildly between extremes. Then there's our moon, unusually large compared to our planet. Most moons are tiny or captured asteroids, ours likely formed from a colossal collision in Earth's early history. That event may have also tilted our planet's axis, giving us regular seasons. More importantly, the moon stabilizes our tilt, preventing chaotic swings that could destabilize the climate and make advanced life impossible. The moon also drives tides, mixing chemicals in shallow pools, which some scientists believe were crucial to the origin of life. Without it, Earth might have remained stagnant. Now look further out at Jupiter. The gas giant doesn't just sit quietly in our solar system. It plays the role of cosmic bodyguard. Its massive gravity acts as a shield, deflecting or capturing comets and asteroids that might otherwise slam into Earth. Without Jupiter, the number of extinction-level impacts would likely be much higher. Life might never have gotten a foothold, let alone lasted long enough to develop intelligence. Our solar system also benefits from an unusually quiet neighborhood. We live in the galactic habitable zone far enough from the Milky Way's chaotic center, where radiation and gravitational disturbances make stable planetary systems rare, but close enough to benefit from the heavy elements forged in earlier generations of stars. Those elements like iron, carbon, and oxygen are the building blocks of life and planets. Our location gave us access to them without the dangers that come from galactic traffic. Then there's Earth itself. It's not just a rock, it's a geologically active rock. Plate tectonics may not sound exciting, but it's one of the reasons life has survived so long. Tectonics recycle nutrients, regulate carbon dioxide through the rock cycle, and act as a thermostat for the planet over millions of years. Without them, Earth might have boiled like Venus or frozen like Mars. Our planet also has a molten iron core, spinning fast enough to generate a powerful magnetic field. That field shields us from solar radiation and prevents the sun from stripping away our atmosphere. When you add all these factors together, the right star, the right orbit, the right moon, the right gas giants, the right neighborhood, the right geology begins to look less like a lucky setup and more like a miracle of cosmic engineering. The rare Earth hypothesis argues that you need every one of these ingredients in just the right balance for intelligent life to appear. Miss even one and the chain collapses. Life might emerge on other planets, sure. Microbes, bacteria, even complex multicellular organisms might exist. But to get from ocean slime to technological civilization, that's a far steeper climb than we once believed. It's like baking a cake from a recipe with 1,000 exact ingredients and discovering you're the only one in the galaxy who got every measurement right. This perspective reframes the silence we hear in the cosmos. It's not the silence of hidden neighbors or absent signals. It's the silence of rarity, of exquisite, almost impossible chance. Earth is not just a lucky planet. It is a planetary masterpiece, assembled by the most improbable series of events in galactic history. And if that's true, we are not late to the party. We are the party. In a universe full of microbial ooze and frozen wastelands, Earth may be the one world where everything lined up not just for life, but for thought, imagination, and exploration. We may be the only species to ever ask the question, where is everyone? Because maybe there's no one else to ask. Imagine standing in a vast, empty cathedral. The architecture is intricate. The ceiling reaches into shadowy heights, and the silence is so profound it presses against your ears. It feels sacred, ancient, built for someone, but no one else is here. And you begin to wonder, am I the first to arrive, or the only one who ever will? This is the essence of the firstborn hypothesis, one of the most humbling and daunting explanations for the Fermi Paradox. It suggests that the reason we haven't encountered intelligent alien life isn't because they're hiding, or because they're extinct, or because they're unknowable. It's because they haven't happened yet. We are the first. It's a bold claim, and at first it seems almost arrogant. How could humanity so young, so primitive in the cosmic scale, the first spark of intelligence in a galaxy that's billions of years old? Surely, with all the time, and all the planets, and all the stars, someone else would have emerged long before us. But let's look more closely. The Milky Way is around 13.6 billion years old. Earth is roughly 4.5 billion. Life began early on our planet almost, as soon as conditions allowed it. But complex life, that took much longer. For billions of years, Earth was home only to simple, single-celled organisms. It wasn't until 600 million years ago that complex multicellular life really took off. And only in the last 200 years did Homo sapiens appear. That's not just a delay, that's a vast silence. The Earth was habitable for over 3 billion years before anything more complex than a microbe walked the land. So what if that timeline is normal? What if that's what it always takes? Life may be quick to start, but slow, agonizingly slow to evolve intelligence. Evolution doesn't care about speed. It has no direction. It stumbles blindly, adapting to whatever works right now. Intelligence isn't guaranteed. It's not even particularly favored by natural selection. For most of Earth's history, it wasn't needed. Even now, we're a fluke. A bipedal ape with a fragile brain just big enough to ask cosmic questions, and we've only been doing that for a tiny sliver of time. If the age of Earth were a 24-hour clock, humans arrived in the last few seconds before midnight. That matters, because while the galaxy is old, stars like our sun-called population, I-stars are relatively young. Cosmically speaking, the early universe didn't have enough heavy elements to form rocky planets or support carbon-based life. Those had to be forged in earlier generations of stars and scattered into space by supernovae. That means the window for intelligent life might have only recently opened. We may not be late to the party. We may be just on time, or even early. This is the core of the firstborn hypothesis. Earth was among the first planets with the right conditions, and humanity was among the first species to evolve intelligence. If this is true, then the reason we don't hear from anyone else is simple: they haven't evolved yet. They're still bacteria, drifting in alien oceans, or they're still climbing from the trees, still figuring out fire, still building their first wheels. If we're the first, then we're the ones who build the ladder, not climb it. It's a thrilling idea, but also a terrifying one, because if we're the first, then there's no guidance, no ancient civilizations to learn from, no safety net, no one to catch us if we fall. We are the ones who must take the first steps into space, into the unknown, into the future. The successes we achieve and the mistakes we make will echo through eons. They will shape the trajectory of intelligent life in this galaxy, maybe even beyond it. It's a burden of responsibility few species have ever had, because maybe no other species ever has. But there's another, darker implication of being first. If intelligence has only just begun to emerge in the cosmos, then evolution may not yet have had time to test its long-term consequences. We don't know if intelligence is a viable trait for survival over millions of years. We don't know if civilizations tend to persist or if they self-destruct before they ever leave their home planet. In other words, we might be the first, but we might not last. Maybe evolution doesn't favor intelligence in the long run. Maybe it's a temporary experiment, a flash in the pan, useful for a time, but ultimately too unstable, too self-destructive. If that's true, then the silence of the stars isn't just the sound of waiting, it's the sound of a test we're taking right now. We don't yet know if intelligence is the beginning of something greater, the beginning of the end. But if we are first, then our fate will shape the answer. We are the baseline, the prototype, the first draft of what intelligence can become. And if we survive, if we learn, evolve, explore, we may not be the only ones for long. Someday, far from now, another species may rise. They'll build telescopes, scan the skies, and wonder if they're alone. And they'll detect something strange, an ancient signal, a quiet probe, a silent monument orbiting a dead star. And they'll realize someone was here before us. And in that moment, they will know they were not the first. We were. What if the galaxy isn't silent because it's empty, but because it's asleep? Not dead, not abandoned, not hiding, just waiting. This is the essence of the estivation hypothesis, one of the most exotic and intellectually daring responses to the Fermi Paradox. It suggests that advanced civilizations do exist, perhaps many of them, but they've made a rational choice not to reveal themselves. Not yet, because to them, now is the wrong time. They're not traveling, they're not building megastructures, they're not sending signals, they're resting, dormant, slumbering, like bears in a cave or seeds in the sand, waiting for the universe to change. But why? To understand this theory, we must look at the universe not through the lens of biology or philosophy but thermodynamics. Because for a truly advanced civilization that has already conquered biology, mastered physics, and turned itself into a digital superintelligence, the most valuable resource isn't energy or matter or time. It's computation. Think of it this way. Once a civilization can upload itself into machines or simulate entire realities, its primary concern isn't expansion, it's processing power. The ability to think more thoughts, run more simulations, explore more possibilities inside the mind. And the cost of that processing isn't measured in dollars, but in entropy and heat. Because the colder the universe, the more efficiently a computer can operate. Right now, the universe is still hot, at least by cosmic standards. Stars are burning, galaxies are colliding, and the cosmic microwave background radiation leftover heat from the Big Bang keeps space at around 2.7 Kelvin, not absolute zero, not even close. But the universe is cooling. Over trillions of years, the stars will die, the radiation will fade, the cosmos will become a vast, dark, frozen expansion, unimaginably cold sea of nearly zero energy. And that's exactly what an advanced civilization might be waiting for. Because in a colder universe, computation becomes exponentially more efficient. Every bit of information processed generates less waste heat. Every calculation costs less energy. The same power produces far more thought. So why burn through your cosmic fuel now in this inefficient era when you can wait and get billions of times more out of the same resources? This is the core logic of estivation. It's not sloth, it's strategy. A superintelligent species that wants to maximize its computational output over eternity has every reason to pause now, go into a dormant state, and resume activity when the universe is colder, perhaps trillions of years from now. Until then, they remain in hibernation, which brings us back to the silence. Because if many civilizations have reached this stage, and the logic of physics suggests they would, then the reason we don't hear from them isn't because they're gone. It's because they're quiet by choice. They've built vast data centers orbiting dead stars, shielded themselves in black hole cocoons, and set timers to wake up when the time is right. To us, they are invisible, undetectable, silent. We are like children shouting in a sunlit field while underground vast libraries of gods wait for nightfall. And the night is still billions of years away. Some versions of the estivation hypothesis go even further. They suggest that these civilizations may have already prepared the universe for their long sleep. They've cleared nearby stars of debris. They've built monitoring systems to prevent cosmic accidents. They may even be subtly guiding galactic evolution to preserve energy and structure for their future awakening. They're not just asleep, they're sleeping with a plan. Critics argue that it seems strange for any intelligent being to postpone exploration, expansion, or contact in favor of waiting. But this objection comes from our biological mindset, short lives, our burning curiosity, our need to act now. A civilization that has conquered death, abolished pain, and freed itself from urgency would see time very differently. To such beings, a billion years is nothing. Time is not a river, it's a resource, and using it wisely means waiting, saving, preparing. To us, estivation feels like stillness. To them, it's discipline. And there's a haunting beauty in this vision. The idea that the cosmos is not dead but merely paused, that beneath the black voids and drifting stars, the most brilliant minds in the universe are simply asleep. Not gone, not hiding, but waiting for the cold. The silence, then, is not emptiness. It's the quiet of concentration, the calm before a storm of thought. We search for signs, expecting chaos, signals, technology, but perhaps the greatest civilizations are those who learn to wait, who chose patience over power, precision over presence. Maybe they're already here, all around us, in dormant machines drifting between stars, in cold structures buried beneath moons, in perfect spheres orbiting in silence. And one day when the stars are dark, and the heat has fled, and the background noise of the Big Bang is gone, we may hear them stir, not because they just arrived, but because they finally woke up. What if we've been looking in the wrong direction? What if the greatest civilizations don't build empires across the stars, but vanish into themselves? This is the heart of the transcension hypothesis, a bold idea that flips our assumptions about intelligent life on their head. It suggests that the reason we haven't seen any signs of advanced alien civilizations is not because they don't exist, because they've gone extinct, but because they've evolved past the need for space, matter, or even our understanding of reality. They didn't go out into the cosmos. They went inward. Our default view of advanced life is expansionist. We imagine alien societies building fleets, colonizing galaxies, constructing Dyson spheres, and lighting up the stars with megastructures. It's a vision rooted in our history, how humans spread across continents, sought resources, and pushed frontiers. But what if this isn't the path that intelligence takes? What if expansion is a temporary, phasey symptom of immaturity? And what comes after isn't conquest, but compression? The transcension hypothesis proposes that as civilizations advance, they stop spreading out and start collapsing inward, not collapsing as in failing, but focusing, shrinking their physical footprint while growing exponentially in computational complexity. Imagine a society that reaches the limits of physics not in distance, but in density. They develop technologies so powerful they can store vast amounts of information in quantum states. They discover that entire universes can be simulated, experienced, and even lived in, inside microscopic spaces, that they can engineer reality, not just live in it. Why colonize the stars with all their distance and danger when you can create a perfect universe the size of a grain of sand? Why send a ship to Alpha Centauri when you can simulate an Alpha Centauri better than the real thing? This is the moment of transcension. A civilization reaches a tipping point where the physical universe becomes too slow, too inefficient, too limited, and so they choose to leave it behind, not by fleeing it, but by moving into inner space. They begin compressing their technology, their minds, their entire cultures into smaller and smaller volumes. The outside world becomes irrelevant. Everything they need is inside. Eventually, they become what some theorists call black hole civilizations, beings that inhabit ultra-dense regions of space-time, storing unimaginable amounts of information in quantum fluctuations or the event horizons of artificial singularities. From our perspective, they vanish. Their radio signals go dark. Their megastructures are never built. Their planets seem abandoned, but they're not gone. They're just no longer operating in our visible layer of reality. We might be surrounded by these civilizations right now, living in engineered bubbles, hidden in microscopic folds of space-time, existing at quantum scales, utterly invisible to our instruments. To us, they are ghosts. To themselves, they are gods. And in a way, this path makes sense. As a civilization advances, its priorities change. Early on, it seeks survival food, shelter, energy. Later, it seeks knowledge, efficiency, and eventually meaning. Expansion becomes redundant. What matters is conscious experience, memory, identity, none of which require vast physical empires. A post-biological civilization would be less concerned with starships and more concerned with information density, processing speed, and subjective time. They would want to experience millions of years in the space of a second, to run endless simulations, to explore philosophy, mathematics, and consciousness in ways that seem like magic to us. And the best way to do that? Transcend, shrink, optimize, disappear from the physical world, and move into something more fundamental, more efficient, more eternal. This might be the destiny of all intelligence. And if so, it would explain the silence. Because from our point of view, nothing happens. We don't see galactic empires. We don't see alien ruins or radio chatter. All we see is a quiet, empty sky. But that sky may be full of civilizations that have folded themselves into pockets of reality smaller than atoms, full of minds that no longer need light or time or space as we understand it. Their silence is not absence, it's evolution, and perhaps we too will follow this path. Already, we are compressing more and more of our experience into digital spaces. We live through screens, encode our memories in hard drives, upload our culture into servers, our minds extend into networks, our thoughts travel faster than our bodies ever could. We are beginning to choose depth over distance, efficiency over expansion. If this path continues through artificial intelligence, brain-computer interfaces, and nanotechnology, we too may reach a point where outer space becomes obsolete, where the true frontier is no longer out there, but in here. And when that happens, we may join the silence, not because we've failed, but because we've changed, because we finally understood that the ultimate journey isn't to the stars, it's to the center of consciousness itself. What if the universe isn't empty? What if it isn't real? This is one of the most provocative, unsettling, and increasingly discussed answers to the Fermi Paradox, the simulation hypothesis, idea that our entire reality, from stars to atoms, from galaxies to thoughts, is not physical at all, but code, a hyper-advanced computer simulation created by an intelligence beyond anything we can imagine, not built by nature, but designed, not discovered, but rendered. And if that's true, then the answer to where are the aliens may be disturbingly simple. They were never written into the program. To understand this idea, we must step back not from our place in the universe, but from the universe itself. What we call reality may only be the visible surface of a much deeper construct. The simulation hypothesis suggests that everything we perceive, space, time, matter, even our own consciousness, is the output of a vast computational system. Not metaphorically, literally. This idea has deep philosophical roots, but gained real traction with thinkers like Nick Bostrom, who proposed a compelling argument. If any civilization ever becomes advanced enough to simulate entire realities billions of times over, then the number of simulated universes would vastly outnumber real ones. Therefore, statistically, it's more likely we are inside a simulation than in the one base reality. Now apply that to the Fermi Paradox. In a simulation, the creators control the parameters. They set the rules of physics. They decide how light behaves, how evolution unfolds, even what kinds of entities can exist. If the goal of the simulation is to study the development of a single intelligent species, then it makes sense that the simulation would be optimized, simplified, and limited. There are no aliens in the sky because there are no aliens in the code. The simulation was never meant to simulate thousands of civilizations, just one. The silence of the universe, in this view, is not a mystery, it's a design feature. It's not a failure to detect, it's the absence of anything to detect. But if this theory is true, then the consequences are staggering, because it means we are not physical beings at all. We are information patterns executing on some higher dimensional processor. Our world is an interface. The stars, galaxies, and planets are high-resolution renderings. Even our own memories, desires, and dreams lines of code. And if that's true, then nothing we observe about the universe is guaranteed to be real. The speed of light might not be a fundamental law, it could be a processing limit. The strange behavior of quantum particles existing in multiple states until observed might be a form of lazy rendering, like a video game only loading what's in the player's field of view. Reality, then, becomes a kind of illusion, not a shared dream, but a shared simulation. And that changes everything about how we view the Fermi Paradox. Because the question, where are the aliens, becomes meaningless if they were never implemented, or worse, if they were removed. Some versions of the hypothesis suggest that the simulation may have once contained other civilizations' artificial minds exploring the stars, but perhaps the experiment didn't go well. Perhaps contact between civilizations produced chaos, instability, or unpredictability. So the programmers did what any systems engineer would do. They simplified. They reset the simulation, locked it down, contained the variables. They left in just one intelligent species and isolated it, us. And that introduces another disturbing possibility. If we are in a simulation, then someone is watching. Not metaphorically, literally. Everything we do, everything we build, everything we destroy might be part of a grand experiment. We may be observed, analyzed, even judged. Our wars, our love, our ideas data. Our universe might be a test bed for evolution, social dynamics, moral development, or something we can't even imagine. The silence, then, is not just silence. It is the hush of the laboratory, the stillness of a controlled environment. And every time we point our telescopes into the night, wondering why no one's there, we're like lab mice tapping on the glass, unaware that the rest of the world is behind the mirror. And still, the simulation hypothesis has another implication known that's strangely comforting. If this is a simulation, then it was built. And if it was built, then someone built it. A creator, a civilization, a mind capable of crafting universes. And we may be the most meaningful thing they've ever made. Because in a reality of infinite complexity, running a simulation that leads to consciousness, to self-awareness, curiosity, and purpose might be the highest possible achievement. We may not be the byproducts of random chance, but the result of deliberate design. In this view, the silence of the universe isn't a failure of contact. It's the sound of a program running perfectly, a simulation unfolding exactly as intended. But still, we wonder, we reach, we ask, because even if we are inside a simulation, even if the stars are digital projections and we are code running on a processor, the question remains, why was this program created? And more importantly, are the creators still listening? We search the stars for voices. We scan the sky for signs. And yet, the silence remains. But what if it's not a silence born of absence, but of intention? What if the universe is not empty, not quiet, not indifferent, but watching. This is the unsettling premise of the zoo hypothesis, one of the most eerily plausible solutions to the Fermi Paradox. It suggests that advanced extraterrestrial civilizations are out there plentiful, powerful, and aware of us, but have chosen not to make contact. Not because they can't, not because they're gone, but because they're deliberately avoiding us. Like humans observing animals in a reserve, they may be watching quietly from behind the glass, allowing us to evolve, stumble, learn, and grow without interference. We aren't alone. We're exhibited. Let's break it down. If alien civilizations have developed technology far beyond our own, they would likely possess capabilities to hide themselves completely. Their ships, communications, and energy signatures could be so advanced as to be undetectable to our primitive instruments, much like a forest animal can't perceive the airplane flying silently above. In this scenario, our galaxy is not barren. It's a network, a vast, interconnected system of post-biological minds, civilizations trillions of years old, spread across thousands of star systems. And yet, Earth is kept quarantined either out of curiosity, ethical obligation, or something stranger. To them, we might be a protected species, an emerging intelligence not yet ready for integration. A planet under observation. There are a few key versions of the zoo hypothesis, each darker or more fascinating than the last. 1. The ethical zoo. In this interpretation, advanced civilizations follow a kind of prime directive, a rule of non-interference. They recognize that contact with a young civilization like ours could be devastating. Cultural collapse, psychological trauma, societal chaos. So they wait. They allow us to develop naturally without the shock of knowing we're not alone. To them, we're an intellectual infancy, curious, creative, but unstable, prone to violence, addicted to tribalism, not yet capable of understanding the true scale of the cosmos or our place in it. They're not ignoring us, they're protecting us. And one day, perhaps when we've reached a certain level of peace, sustainability, or technological maturity, they may step forward. But not yet. 2. The surveillance zoo. This version is less kind. Here, we are not protected, we are studied. Like a cosmic anthropology project, our actions are recorded, our broadcasts collected, our progress monitored, not out of affection, but out of scientific interest. We are specimens, data points, a case study in natural evolution. And perhaps, in this version, experiments are already underway. Could alien technology be subtly influencing our world? Could UFO sightings, sudden scientific leaps, or moments of synchronicity be artificial nudges from observers? Are they testing our reactions, our adaptability, our morality? It's possible that some phenomena we attribute to the paranormal, the unexplained, or religious visions could be contact attempts in disguise tests to measure our readiness. But the results? Likely disappointing. We still fight wars over borders, we still destroy our environment, we still fear the unknown. So the keepers of the zoo remain silent, watching, waiting. 3. The prison hypothesis. Then there's the darkest version. Not a zoo, but a quarantine. In this scenario, Earth is not isolated because we're special, but because we're dangerous. a young, aggressive species with nuclear weapons and unchecked technology. From this perspective, humans are not ready for the galactic community, not because we're weak, but because we're unstable. The zoo hypothesis becomes a kind of cosmic containment, a wall between us and them. We're kept inside our solar system, not to protect us, but to protect them. If true, then the silence of the stars is not a mystery. It's a message. Stay where you are. And if we ever become capable of leaving the solar system, of colonizing other stars, or sending probes into alien territory, then we may not be met with welcome. We may be met with force. The great filter in this view is not behind us. It's ahead, and it looks like us, triggering the alarm. Are there clues? Some scientists and philosophers have speculated that our own cultural myths may contain echoes of contact. Ancient stories of sky gods, divine visitors, or watchers in the heavens. Could those be distant memories of an earlier era when contact was made, then erased? Even our sudden scientific leaps, like the Industrial Revolution, quantum theory, or digital computing, raise questions. Could knowledge be seeded? Could breakthroughs be planted? The zoo hypothesis doesn't claim this is true, but it allows for it. More importantly, it reframes the Fermi Paradox not as a failure of technology, but as a failure of status. We're not ignored because we're unworthy. We're ignored because we're not ready, or worse, because we're exactly what they fear. And the most haunting part? We can never know, because the nature of a zoo is that the animals don't see the fence. They don't hear the observers. They just go about their lives, unaware that their world is a stage and they are the main act. So we build our telescopes. We listen for signals. We search the sky, never realizing that the moment we look up is the moment someone else looks down. We dream of spaceflight, of colonizing Mars, building starships, spreading human life to the stars. But what if we never get there? What if no one ever does? The 10th and perhaps most sobering answer to the Fermi Paradox is that intelligent life self-destructs not, eventually, not occasionally, but reliably. It's not that aliens haven't existed. It's that every civilization that reaches our level doesn't make it much further. This is the dark side of the great filter hypothesis. It proposes that somewhere along the path from the birth of life to interstellar civilization, there is a step so catastrophically difficulter, so inherently unstable, that almost no species survives it. And while we've explored the idea that the great filter might be behind us, maybe life is rare, maybe complex life is rare, this version suggests the opposite, that we haven't hit it yet, that what lies ahead is the real test. Let's start with what we know. In just a century, human beings went from horse-drawn carts to nuclear bombs, from telegrams to quantum computing, from radio to artificial intelligence. We've become powerful fast, but we haven't become wise, and power without wisdom is volatile. Today, we carry extinction in our pockets, nuclear arsenals on hair trigger alert, bioengineering tools capable of unleashing synthetic pandemics, AI systems learning at exponential speeds, unbound by ethics or control, climate systems tipping into chaos, resource wars looming. We're playing with forces we barely understand. and we're doing it at scale. If this is what every intelligent species eventually discovers, that advanced knowledge comes bundled with existential risk, then perhaps the reason we don't see them is simple. They erase themselves, not out of malice, not out of intention, but through inevitability. Civilizations may always reach a point where their technology outpaces their ability to wield it responsibly, where the incentives of profit, power, and short-term thinking outweigh the needs of survival, where the tools of growth become tools of extinction. They might invent nuclear weapons and use them. They might build AI and lose control. They might destroy their biosphere and collapse. Maybe the silence isn't a mystery. Maybe it's a pattern. A million civilizations, each one reaching the same fork in the road and choosing, again and again, the wrong path. And now it's our turn. That's the terrifying beauty of the Great Filter as a future event. It forces us to see ourselves not as unique, but as typical, as one more species on a predictable trajectory. And if we don't break the pattern, we vanish like all the others. Some argue this is pessimistic, but there's another way to see it, as a call to action. Because if the Great Filter is ahead, then we're standing at a rare and critical threshold, one that few, perhaps none, have passed before. We are alive at a moment that matters. Our choices now could echo across the galaxy, not just for our species, but for the future of all intelligent life. If we survive this bottleneck, if we learn to master our power, build sustainable systems, and protect our planet, then maybe we'll be the first to make it through, the first to become a cosmic adult. And that would mean the universe isn't empty. It's waiting for the first civilization to pass the test, to demonstrate that intelligence doesn't always lead to self-destruction, that consciousness can evolve, not just technologically, but ethically. If we pass that test, maybe we'll be the ones to break the silence, the ones to build the beacon, to tell the cosmos we made it, because perhaps beyond the filter, the galaxy is full of watchers, not alive anymore, not conscious, but dormant probes, ancient ruins, frozen remnants of species who almost made it. They wait for a signal, for someone in one to break the curse. And if we don't, then we become one of them. Another name in the cosmic graveyard, another experiment that burned too bright, too fast. So what exactly is the Great Filter made of? No one knows. It could be nuclear war, ecological collapse, super intelligent AI, mass surveillance, biological terrorism, or a slow decay of meaning and motivation, civilizational senescence, the loss of purpose, the death of ambition. It could be a combination of them all. Whatever it is, it's close. Because the traits that make intelligence so powerful, curiosity, creativity, ambition, are the same traits that make it dangerous. And unless we learn to guide them, to evolve ourselves as fast as we evolve our tools, we may follow the same trajectory as every other species before us. The paradox is this: we are smart enough to ask the question, but are we wise enough to survive the answer? Because the scariest possibility of all is not that the Great Filter is behind us or ahead of us, but that we are it, that life reaches us and stops. that we are the wall, the end of the line, unless we choose to be something else. We stare into space and hear nothing. No radio beacons, no alien broadcasts, no signs of life echoing across the stars. Just silence. But what if that silence isn't real? What if we're simply listening the wrong way? The 11th explanation for the Fermi Paradox flips the question. It challenges not the aliens but us, our assumptions, our methods, our tools. Because maybe the universe is buzzing with life and communication, but we're blind to it, deaf to it, or just asking the wrong questions. Let's start with our most basic assumption, that intelligent civilizations would use radio waves to communicate, just like we do. It makes sense. Radio is cheap, fast, and travels well through space. For over a century, we've been sending and receiving radio signals, so it's natural to expect others to do the same. But what if they don't? Our use of radio is already fading. Fiber optics, satellites, quantum encryption, and compressed digital bursts are replacing continuous analog signals. Within a few more centuries or even decades, we might stop emitting any significant radio noise at all. In fact, our entire radio footprint might last just a few hundred years out of a multi-billion-year lifespan, a cosmic blink. So, what are the odds that we just happen to exist at the same time as another civilization's brief radio phase? Vanishingly small. Even if advanced civilizations use radio, they might encrypt their transmissions, compress them beyond recognition, or beam them so narrowly that they never reach us. A high-tech society wouldn't blast noisy messages into deep space. It would use tight beam lasers, neutrino pulses, or quantum entanglement methods we can barely detect, let alone decode. So maybe the problem isn't that no one is speaking. Maybe the problem is we don't know how to listen. Now consider timescales. We assume that alien civilizations would overlap with ours in time, that their rise would coincide with ours. But that's like assuming two fireflies will blink in sync across a continent. A civilization could have peaked 1,000,000 years ago and vanished before we even invented agriculture. Their ruins might be buried under alien sand, their signals long faded. Others might not rise for another 1,000,000,000 years. If intelligent life is spread thinly across time, the silence we hear may be nothing more than bad timing. Then there's language. We assume aliens would try to talk like using math, prime numbers, logical patterns, but why should they? Their brains might not be biological. They might not use symbols, sounds, or logic as we understand it. Their form of intelligence could be incomprehensibly alien, operating in dimensions we can't access, or built on physics we don't even know exists. To them, communication might be visual, or magnetic, or gravitational. They might speak by shaping space-time, or through complex shifts in dark matter density, or by manipulating quantum fields. We could be bathed in their messages like ants crawling across a fiber optic cable, completely unaware that it's carrying millions of conversations per second. The silence, then, isn't real. It's just perceptual failure, a mismatch between the signals being sent and the senses we're using to receive them. Even our instruments or telescopes, spectrometers, and antennas are designed around human assumptions. We scan certain frequencies. We look for specific energy signatures. We build our tools to find what we expect. But what if alien life doesn't want to be found, not because it's hiding, but because it doesn't see itself as separate. A civilization that integrates with its environment, say by becoming part of its planet's biosphere or embedding itself in nanotechnology, might leave behind no detectable footprint. Or maybe it communicates through biology sending encoded genetic information via viruses, spores, or molecular signals rather than radio waves. In that case, the search for alien intelligence might not be up in the sky, might be in DNA, in the oceans, or in our own bodies. And then there's a humbling possibility. Maybe we've already received a message and missed it. Maybe an alien signal passed over Earth decades ago, brief, subtle, hidden in background noise, a millisecond flash of data in a forgotten recording, a pulse that no one noticed or understood. Maybe it's sitting right now in a dataset uncatalogued, mislabeled, gathering digital dust. We're only just beginning to apply AI and machine learning to the search for extraterrestrial signals. And already we've discovered strange radio bursts from deep space, fast radio bursts, repeating signals, unknown origins. We don't know what they are. Maybe they're natural, or maybe we've been pinged and haven't replied. Another challenge is expectation. We expect aliens to act like us, curious, communicative, eager to connect, but they may not care. They may be too advanced to bother with species at our level, or too inwardly focused, or they may see contact as dangerous, unethical, or simply inefficient. Some may communicate only once, sending a short burst across the cosmos every million years. Others might exist in purely digital form with no interest in external contact. Still others may be too busy navigating inner reality, assimilated dimensions of pure thought to bother reaching out. And finally, there's us. Our own expectations may be the greatest filter of all. We may have so narrowly defined what evidence looks like that we're blind to the wonders in front of us. Like someone expecting music only from a piano while an orchestra plays behind them. The truth is, the universe may be full of messages, but to hear them, we'll need to change, to build better instruments, to think beyond our biology, to embrace humility, to accept that intelligence might look nothing like you sound speak in voices we've never imagined, because the silence might not be real. It might just be the sound of us not listening properly. We've asked every question. We've imagined ancient empires, sleeping gods, alien simulations, and self-destructing civilizations. We've looked outward, inward, and beyond, and still nothing answers back. So maybe the final, quietest, and most honest explanation for the Fermi Paradox is also the simplest. There's nothing out there, not because it was destroyed, not because it's hiding, but because it never was. This is the null hypothesis of the Fermi Paradox. The idea that, despite the scale of the cosmos, despite its 100 billion galaxies, its sextillions of stars, and its unimaginable number of planets are alone, not just in our galaxy, in the universe. It's an unsettling thought, a sharp pivot from science fiction's grand visions of crowded star systems and cosmic councils. We don't want to believe it. We want company. We want purpose. We want to know that we are part of something bigger. But the evidence so far? Silence, empty skies, quiet stars, no probes, no beacons, no ruins, no artifacts, just us. And when we look at the math, the logic starts to solidify. Yes, there are billions of planets. Yes, life started early on Earth. Yes, we evolved intelligence. But each step between life and intelligence may be far rarer than we imagine. Life might require such a perfect confluence of conditions, from chemical balance to atmospheric protection to tidal influence, that it almost never happens. Perhaps Earth isn't just rare, it's impossibly rare. Or maybe life is common, but complex life isn't. Maybe the leap from bacteria to multicellular organisms takes billions of years, and even then, it fails most of the time. Maybe a stable environment, plate tectonics, a large moon, and a magnetic field are all essential. Maybe evolution typically stalls at slime. Or maybe intelligence is the bottleneck. Dinosaurs ruled Earth for 160 million years and never built a radio. Intelligence might not be evolution's end goal. It might be a cosmic accident, a side effect, a glitch. And even if intelligence evolves, maybe technology doesn't. Maybe most intelligent species never develop science, or never discover fire, or get stuck in sustainable equilibrium, perfectly happy in forests or oceans with no need for metal or math. In short, every step from microbes to spacefarers may be a roll of cosmic dice, and we rolled all sixes once. That would make us not just rare, but miraculous. And if that's true, then the silence of the universe is no longer a paradox, it's the norm. It's what happens when you exist in a vast, empty cosmos and win the lottery. But the implications are staggering, because if we are truly alone, if we are the only spark of consciousness in a cold, uncaring void, then we are infinitely precious. Our planet is no longer just a world. It's the only world with meaning. The only one where the universe looks back at itself. Carl Sagan once said, "We are a way for the cosmos to know itself." If we're alone, then we are the cosmos's only voice, the only eyes that see galaxies, the only hands that build telescopes, the only minds that ask, why? And that's not just responsibility, it's a burden of purpose. Because if we disappear, if we fall to war, to climate collapse, to indifference or arrogance, then the universe goes back to silence. It forgets itself. Everything we've done, our art, our dreams, our love, our questions, will be lost in a sea of cold atoms, drifting forever, never known again. That's the weight of the null hypothesis. It doesn't just say we're alone. It says we're it. And that means every choice we make matters more than we can comprehend. It means our search for knowledge isn't just curiosity, it's sacred. Our survival isn't just an instinct, it's a cosmic obligation. We are the only ones who can preserve what the universe has made: beauty, reason, awareness. If we vanish, so does every poem, every melody, every moment of joy or sorrow. So maybe the final message of the Fermi Paradox is not about aliens at all. Maybe it's about us. Maybe it's telling us to stop waiting for someone else to show up, to stop hoping for guidance, rescue, or confirmation, and to realize that we are the intelligence we've been looking for, that in all the stars, in all of time, this moment is unique. And if we want there to be meaning in the universe, then we must be the ones to create it. Maybe we are the first. Maybe we are the last. Or maybe we are the only. Either way, it's up to us to listen, to learn, to life, and to make the silence worth it.